All right. Hello, everyone. I just wanted to make a quick video for exponent rules for you. I'm not going to have time to cover exponent rules in class. This is something I'm sure you've seen um, several times before, probably. But just in case you needed a refresher, if it's been a while, I wanted to go through the exponent rules and just give you a video to help you if you need it. So let's start with exponent rules. If we're multiplying two exponential expressions with the same base here, like x to the a times x to the b, sorry here. Okay, like here, x to the a times x to the b. What you're going to do is you're going to add those exponents in that case. So this becomes x to the a plus b. Keep the same base and add your exponents. You can do this when the bases match. The fact that both of those bases are x is important there. Similarly, if we are dividing two exponential expressions with the same base, x to the a divided by x to the b, as long as those bases are the same, we can combine these, and to do that, we subtract our exponents. So that becomes x to the a minus b power. If we have powers, two powers, here, like if we have x to the a power, that whole thing to the b power, in that case, you're going to multiply the exponents to simplify this. So that becomes x to the a times b power. And then what if we have an exponent on quantities? How do we simplify those? Um, As long as it's just multiplication or division inside the parentheses, then everything in here can get that exponent. We can distribute that exponent across multiplication or division. So here in this first one, x to the a times y to the b, that whole thing to the c power, we can distribute this exponent of c to each piece. And because it's a power to a power, we get x to the a times c, and that whole thing times y to the b times c power. We multiply our exponents because we have powers to powers. And each of the things in parentheses gets that exponent since they're connected by multiplication. Similarly, if the two things are connected by division, sorry, I'm not sure why there's an extra equal sign in here, so just pretend that's not there. X to the a over y to the b, that whole thing to the c power. Since it's just division in here, again, each of these pieces can get that exponent of c. We can distribute it to each piece. And because we have powers, two powers, we'll multiply the exponents. This becomes x to the a times c power all over y to the b times c power. And then what if in parentheses the things are connected by addition? If we have addition inside parentheses, you cannot distribute that exponent. Addition and subtraction ruin a lot of different algebraic maneuvers. Because of this addition, we cannot distribute that exponent. There's nothing to do here. So I want you to know that in this case, just leave it as is. There's absolutely nothing to do to simplify here. I'm not going to kind of test you on that. I just wanted to make sure I made clear when you can apply these properties and when you can't. That's an important thing to realize. Okay, last couple exponent rules before we do some more examples. Anything to the 0 power is 1. I get a lot of questions about why that is. And to kind of help you understand that, I kind of like to think about it as a ladder. So if I think about 5 to the first power, well, we know that that's 5. And then if I go up the ladder and I increase my exponent by 1, then 5 to the second power is this 5 times 5, which is 25. If I keep going up, 5 to the third power is 5 times 5 times 5. Well, 5 squared was 25. I'm going to multiply by 5 again to get 125. And similarly, 5 to the fourth is 5 to the third, which is 125 times 5, 625. And you can keep doing that on up the ladder if you wanted to. Now, just like we can go up the ladder, we can also come down the ladder. So to get from 5 to the fourth to 5 to the third, we would divide by 5. So 625 divided by 5 is 125. That's how we come down the ladder. And so to get to 5 to the 0 power, we decreased the exponent by 1. We're going to divide by 5 to come down the ladder. 5 to the first was 5. If we take 5 divided by 5, we get 1. This is why anything to the 0 power is 1, because technically to get anything to the 0 power, you have to divide it by itself. And that's kind of our multiplicative base. So anything to the 0 power is 1. And then this will help us in just a minute. But what if we keep going down the ladder? What if I subtract 1 again from my exponent? I'm just going to keep coming down the ladder. So to get 5 to the negative 1 power, I'm going to divide that 1 by 5, and I'm going to get 1/5. Okay, what if I keep coming down the ladder? 5 to the negative 2, I'm going to take 1/5, and I'm going to divide by 5. And so 1/5 divided by 5 is 1/5 times 1/5 when we keep change flip. That ends up being 1 over 25. 5 to the negative third, I'm going to take 1 over 25 and divide by 5, or multiply by 1/5, and I'm going to get 1 over 125. And this will become clear in just a minute. But that's kind of how I like to think about zero exponents and negative exponents, and why they work the way that they do. Okay, so anything to the 0 power is 1, because anything divided by itself gives you 1. So I don't care what it looks like, if it's 5 to the 0 is 1, or negative 18 to the 0 is 1, or 138 times x to the second power times y to the 47th power, all of that to the 0. No matter how scary that thing is, anything to the 0 power is 1. Okay, and the negative exponents, like we can see over here on the right with our ladder, negative exponents gave us reciprocals. It pushes you across the division bar. So you can see to the right here, 5 to the negative 1, that's 1 over 5 to the first power. Essentially what that negative exponent does is says, hey, 5 to the negative 1, you can't be here. I need to kick you out. You're being evicted. You got to go downstairs. And so when you cross the division bar, it can't take the negative with it. And when it comes down to the bottom, it's 5 to the first power. So 5 to the negative third power, again, that's over 1. That negative exponent says, you can't stay here. Get out, cross the division bar, go downstairs. And when it does that, the exponent becomes positive. And when it leaves 1 behind. Anytime with fractions, if something leaves with division, it leaves a 1 behind. And just like over here, that makes sense with what we did before, where 5 to the negative third is 1 over 125. This makes sense with that. What if we have multiple things on the top and the bottom? What if I have x squared times y to the negative third? Well, that's all over 1. And so does everything move here? Does everything get kicked out? Or how do we do this? And the answer is only the things with a negative reciprocal needs to move. So since this x has a positive exponent, it gets to stay where it is. So x squared stays, but y has a negative exponent. That negative exponent says, y, get out of here. You can't stay here. So it has to cross the division bar, and when it does, that exponent becomes positive. If I have multiple things in the same expression that have negative exponents, again, each thing with a negative exponent has to move. Anything with a positive exponent can stay. So x squared can stay. Y to the third gets evicted and it has to move. And z to the negative fourth down here, that also has to move. It gets kicked out of where it is. It has to go upstairs because it doesn't have anywhere else to go. It goes upstairs. And when it crosses that division bar, the negative can't come with it. So that's how we deal with negative exponents. They give us reciprocals. It pushes us to the other side of the division bar of the fraction symbol. Okay, so let's try this. So 2 to the second power, most of us are good with that. That's 2 times 2, which is 4. Now, this guy here, In 2 and 3, I want to make the difference between these clear. One of these has parentheses and one of these does not. The parentheses do, in fact, make a difference. I'm actually going to start with number 3 here. These parentheses say this exponent of 2 applies to the entire number negative 2. This means negative 2 times negative 2. And that makes the whole thing positive 4. It means the exponent applies to both the negative and the 2 because it's the number negative 2, that whole thing squared. Now, this one over here, if we come back to number 2, this negative 2 squared doesn't have parentheses. So if it doesn't have parentheses, this one actually means negative 1 times 2 to the second power. The exponent only applies to the thing right in front of it. If there's no parentheses, it's only the thing in front of it, and that's it. It doesn't apply to any negatives, any numbers, any variables next to it, only the thing in front of it. And so here, this means negative 1 times 2 to the second power. This is negative 1 times 4. This whole thing is negative 4. So these parentheses in between number 2 and 3, these make a big difference, and I want you to be careful with those. All right, so number 4, 2 to the 0 power, that's 1. Anything to the 0 power is 1. Number 5 here, negative 3 to the negative 3x squared. The 2 on the x, that exponent of 2, it applies only to the x because there's no parentheses. This is negative 3 times x squared. That is negative 3x squared. There's no simplification to be done here. And again, sometimes you can use these, sometimes you don't. I want you to be able to recognize when you can and cannot use these rules to simplify. Number 6 here, this now has parentheses. So this is saying the entire number negative 3x squared. So that means negative 3x times itself, which makes the whole thing positive 9x squared. And then here in number 7, this has a negative exponent with it. The negative exponent says you can't stay here. You need to cross the division bar. Go downstairs. And because of the parentheses, it says the entire thing, negative 3x, the entire thing is being evicted. So that means the whole thing, negative 3x, goes downstairs. And when it does that, the exponent becomes positive. It leaves a 1 behind. And notice here, the only negative that you change is the negative in the exponent. Don't touch anything in the parentheses. That just that's what's moving downstairs. So you don't touch anything with that. It's just the negative in the exponent that goes. So this is 1 over the quantity negative 3x, that whole thing squared. That means negative 3x times negative 3x in the denominator. And that means it's positive 9x squared because of what we did in number 6. Okay, this next one, okay, I've got a lot of negatives here. So the negative 2 applies to the whole negative 3x, and then I've got a negative hanging out front. I'm going to write that as negative 1 times the quantity negative 3x to the negative 2. I'll put that all over 1 so I can see the division bar and where everything needs to go. Now, once I write this multiplication out, hopefully it's clear to you. The negative 1 can stay because it has an exponent of 1, which is positive. It gets to stay put. This negative exponent says negative 3x, get out of here, you can't stay here. So negative 3x moves downstairs, and when it does that, its exponent becomes positive. And so again, this negative 1 stays up here. In the denominator, we have negative 3x times negative 3x. That becomes positive 9x squared. That is our answer. All right, we've got a few more to practice just to make sure that we're solid on these exponent rules. And as things get a little more complicated, we can sift through all of this stuff. Number 9, I've got a whole quantity to the 0 power. It's this whole thing to the 0 power, means 5x squared y divided by 5x squared y. That's just 1. Anything to the 0 power is 1. Number 10 looks very similar, but it doesn't have the parentheses. Parentheses make a difference. What this one means is this is 5x squared times y to the 0. That 0 power only applies to the thing in front of it. It only applies to the y. This is 5x squared times 1, or just 5x squared, because just the y to the 0 power gives you 1. In number 11, well, I've got negative 5 to the 0, so that's just 1, right? Because it's to the 0 power. Well, but hold on, there's no parentheses. So this one is actually saying negative 1 times 5 to the 0. There's no parentheses. The 0 applies only to the 5 in front of it. So this is negative 1 times 1, or just negative 1. All right, so let's come to number 12. Okay, so this is where we play should I stay or should I go? We've got a lot of things to different powers, and I've got a negative exponent, which means somebody's going to get kicked out of where they are. We just have to figure out what has to move and what has to stay. Here, the exponent on the 3 here is actually a 1 because there's no parentheses, so that negative 4 exponent applies only to the x, not to the 3. The 3 has its own exponent of positive 1. So should I stay or should I go? The 3 has a positive exponent. It gets to stay put. X to the negative 4th, that negative exponent says, get out of here, x, go downstairs. And when it does, the exponent becomes positive. Y to the 3rd already has a positive exponent. It gets to stay put right where it is. And that's my answer. Number 13. All right, there's a few different things that we can do here. You can apply the negative to the exponent on the outside and push the whole quantity to the bottom and then work with your exponents. Because we have a whole quantity here and everything is just being multiplied, I like to distribute my exponent first just so I don't forget, and then I'll just play should I stay or should I go after that. I like to distribute the exponent before introducing fractions, but that's a personal preference. You can do this in any order that you choose. If you want to put that whole quantity to the bottom and then do the exponents, do you. Okay, so I like to do the exponents first. I want to distribute that. This is all multiplication, so I can do that. So 3, I'm going to have 3 to the negative 2 power. X to the negative 4th to the negative 2, I'm going to multiply those exponents. And y to the 3rd to the negative 2, I'm going to multiply those exponents. So I get 3 to the negative 2, x to the 8th, y to the negative 6th, and then I just need to play should I stay or should I go? 3 has a negative exponent, it gets kicked out. X has a positive exponent, it gets to stay. Y to the negative 6th, that negative exponent kicks it out. And so overall, I have x to the 8th over 9y to the 6th. All right, so in 14, again, I like to apply the negative exponent. I like to apply this exponent to everything inside before I do anything else, but that's a personal preference. This is a choose your own adventure. If you want to do this in a different order, you absolutely can. We should get the same answer in the end. Okay, so I'm going to apply this negative 2 exponent to everything in parentheses. It does not apply to the 3, so the 3 is as it is. And then I'm going to have x to the negative 4th to the negative 2nd. I'm going to multiply those exponents and get positive 8. And then y to the 3rd to the negative 2, multiplying those exponents, I get negative 6. And all over 1, it's time to play should I stay or should I go? 3 gets to stay, x gets to stay, y has to go. And we are all set. Okay, so number 15 here, we've got multiplication and division. This should be m to the negative 2 power. So sorry about that. That's kind of hard to read, but this is actually m to the negative 2 power. That printed kind of strange. Okay, so because I just have multiplication and division inside this fraction, I can distribute this negative 3 to everything in parentheses. And so when I do that, I'm going to get 3 to the negative 3, m to the negative 12th on top, all over m to the positive 6th on top. Again, this is a choose your own adventure. You could have simplified the m's inside before you distribute that negative. It is my personal preference that I just like to apply that exponent and then simplify, but that's just me. And then before I play should I stay or should I go, I've got m's on the top and the bottom. I've got division with variables to powers. So I'm going to go ahead and simplify those as well. So I'm going to get 3 to the negative 3. And then m to the negative 12 divided by m to the 6th. I'm going to subtract those exponents. And so I'm going to get m to the negative 12 minus 6th power. I subtract my exponents when I combine with division. And so when I do that, I get 3 to the negative 3 times m to the negative 18th. And it's time to play should I stay or should I go? Both of these guys have to go. So the 3 to the 3rd will go to the bottom, and the m to the 18th goes to the bottom. And this ends up being 1 over 27 m to the 18th. Sorry, I didn't leave myself a whole lot of room here. Sorry, guys. Okay, so the next one. I've got a lot of stuff going on here. Please excuse my dear Aunt Sally. I'm going to start with the parentheses, and I'm going to distribute this -1 into everything in parentheses. That's, again, not the only thing that you can do here, but that's the way that my brain is going to process this the best. So when I do that, everything on top stays the same. -3 stays on the bottom. And then the -1 only applies to the x to the 4th and the y to the -2. So I'm going to multiply my exponents here. I'm going to get x to the -4th times y to the +2nd. Okay, I have exponents. I have exponential expressions with the same base on top and bottom. So I can divide those guys. And so when I do, I'm going to kind of split this up into pieces here. I can do this because everything is just multiplication and division. And I'm just going to split it up so you can kind of see what I'm doing here. So I've got these numbers. They're going to stay put. When I combine these two, I'm going to subtract their exponents. And I'm going to get x to the -2 minus -4 becomes -2 plus 4. That becomes a +2. And when I get y to the 3rd divided by y squared, I'm going to subtract my exponents, and that becomes y to the 3rd, or y to the 3 minus 2. Subtract your exponents, that becomes y to the 1st. These have positive exponents, so they get to stay on top, and that's my answer. 2x squared y, all divided by -3. All right, last one here. Again, there's a few different ways that you could do this. You can combine those p's beforehand and subtract your exponents and then apply the exponent on the outside, but my brain doesn't like that as well because it's all multiplication and division inside this set of parentheses. I can distribute that -2 to everything in there, and that's where my brain likes to start. So that's what I'm going to do. So when I multiply these exponents, because I've got powers, 2 powers, I get p to the -4 times -2. That becomes +8 over 4 to the -2 power times p to the -5 times -2. That becomes +10. Okay, now I can combine the p's here. P to the 8th divided by p to the 10th. I'm going to subtract those exponents, and I get p to the 8 minus 10. That's -2 power. And then I still have that 4 to the -2 on the bottom. So just a heads up, when you combine and you subtract the exponents on a variable, whatever you get, put that thing on the top. So if it's positive, like here when we did in number 16, when we did x to the -2 divided by x to the -4th, and we got x to the 2, you put it on top. It doesn't matter whether your exponent's positive or negative. Whatever you get when you subtract those exponents, put that thing on top. So here, when I did p to the 8th divided by p to the 10th, and I did p to the 8 minus 10, which is p to the negative 2, I still put that on top with the negative exponent. Just when you subtract exponents, put that thing on the top, and then you can move it from there if it has a negative exponent. Okay, so now I have things with negative exponents. We got to play should I stay or should I go? P to the negative 2, that gets evicted and has to move downstairs. So that becomes p squared on the bottom. 4 to the negative 2, that also gets evicted. It comes up to the top, and that becomes 4 to the positive 2 on top. And this simplifies to 16 over p squared. Okay, one last set of exponent rules before I let you go. These are fractional exponents. If you have fractions as exponents, these give you roots and radicals. Okay, so what I mean by that is, for instance, 4 to the 1/2 power. If I have a fraction in my exponent, these create roots. To the 1/2 power, this number on the bottom creates the index of your root. So this creates a second root of 4. A second root is actually just a square root. And so this means the square root of 4, which is 2. So 4 to the 1/2 power is 2. Okay, so that one was nice, but what if I've got 5 to the 1/2 power? Well, that just means the second root or the square root of 5. That's all the simplification we can do there. That's all that means. What if I have 5 to the 1/3? Because I have a 3 in the denominator now, that creates a cube root. And again, this is the cube root of 5. No simplification we can do there. That's all it means. What if I have numbers on top and the bottom? For instance, what if I have x to the 4/7 power? If I have x to the 4/7 power, this number on the bottom creates the index of the root. So that creates a 7th root. Now, what do I do with the 4 on top? Well, it actually serves as a regular exponent, and it goes underneath the radical with the x. It's x to the 4th. That's what goes inside that 7th root. So this is the 7th root of x to the 4th. Just kind of a fun fact here. You can actually write the 4 as an exponent inside, or you could write it as an exponent on the outside. So this could also be the 7th root of x, that whole thing to the 4th power. That's kind of a just something that you can do. It's not something that we'll do very often, but it is something that you can do. Usually our brains process it better this first way, and I'm absolutely fine with leaving it like that. Okay. And then what if we have, before we kind of keep going here, what if I have something to negative powers, a negative fractional power? So if I have x to the negative 4/7 power, what does that do? Well, the negative says you can't stay here. You need to cross the division bar. So the negative pushes us into the denominator, and your exponent becomes positive, and then we can evaluate that fractional exponent, and that becomes a 7th root of x to the 4th on the bottom. So sometimes you'll have negatives and fractions. The negative still pushes you in across the division bar, and the fraction still makes roots, and they can work together. Okay, so let's practice these guys. The 6th root of x, I want to write that in exponential form. So we have it in radical form, and I want it in exponential form. If we have something in exponential form, I want to write it as a radical. We're just going to go back and forth. So this is a radical, so I want to write it as an exponent. The 6th root of x, that is x to the 1/6 power. This index on the radical, that's what goes on the bottom here. And the power on x here is 1, so that's what goes on top. 1/6 power. Okay, let's try this one. The 4th root of 11 to the 3rd. To write this in exponential form, this is 11 to the let's see, it's a fourth root, so I'm going to put the 4 on the bottom in my fractional exponent, and this 3 goes on top. This becomes 11 to the 3/4 power. Okay, let's do 121 to the 1/2 power. Okay, now this is an exponential form. I want to write it in radical form. The 2 on the bottom creates a second root or a square root, and the 121 goes inside. The square root of 121 is 11. So it's just the square root of 121. B to the 2/3 power. To write this in radical form, the 3 on the bottom creates the index of my root, so that creates a cube root. The 2 goes with the b as an exponent, so this is the cube root of b squared. And finally here, x to the 7/8 power. This 8 on the bottom creates an 8th root. The 7 on the top goes with the x underneath, so this is the 8th root of x to the 7th. All right, a few final things. We can work with fractional exponents the same way we work with anything else. So these look kind of gross. We're going to have to fight through a little bit of arithmetic, but we've got this. So the first thing I want you to do here is turn all of these things into fractional exponent form. So this is going to be y to the 1/6 power times the 4th root of y to the 3rd. That becomes y to the 3/4 power. So I have y to the 1/6 times y to the 3/4 power. I'm multiplying two things with the same base. I'm going to add their exponents. This becomes y to the 1/6 plus 3/4 power. So now I just have to fight through adding 1/6 and 3/4. To do this, I'm going to do a little bit of side work here. I need a common denominator to do this. My common denominator is going to be 12. So 1/6, to get a common denominator of 12, I multiply top and bottom by 2. And 3/4, to get a common denominator of 12, I multiply top and bottom by 3. And 3 times 3 is 9 there on top. And now I can add these, add your numerators and keep your common denominator. So this becomes 11/12. And so this is going to be y to the 11/12 power. And it wants you to write it in radical form. So this would be the 12th root of y to the 11th power. So I'm good with you writing it either way. I believe Alex is going to want the radical expression there. Okay, what if we're dividing? Again, we're going to put everything into exponential form and then work with exponents because we know how to do that. So on top, we have w to the 1/2 power. On the bottom, this becomes w to the 2/6 power. You could simplify and write that as 1/3, but we're combining these two here, and we're going to have to get a common denominator to subtract our exponents anyway. So I'm just going to leave it as 2/6, just because I know I'm going to have to do that anyway. Okay, so now we are going to combine these. We're dividing with the same base, so we subtract our exponents. So I'm going to have to do 1/2 minus 2/6. Again, to subtract fractions, I need a common denominator. My common denominator here will be a 6. So I'm going to have 3/6. I got a common denominator for 1/2. 1/2 is 3/6. And I'm going to subtract from that 2/6, and that gives me 1/6. So this is w to the 1/6 power, which is the 6th root of w. Okay, last one. Again, bring everything to exponents and then go from there. This is x to the 3/4 power times x to the 1/6 power. I'm multiplying with the same base. I'm going to add those exponents. This becomes x to the 3/4 plus 1/6 power. And then I have to fight through the arithmetic of adding those exponents. And actually, this is 3/4 plus 1/6. I actually did that exact same one over here. So I'm not going to redo the arithmetic because I already did this. And so when we added these, we got 11/12. And so this becomes x to the 11 over 12, which is the 12th root of x to the 11th power. Okay. So that concludes a quick, or not so quick, I suppose, refresher of exponent rules. I hope this is helpful for you. We're going to be using exponents in the next couple of weeks, and we're going to have to be thinking exponentially. So this is a great opportunity to kind of get more familiar with these guys. As always, please let me know if you have any questions, and I hope you have a great day.